Hello everybody, Ryan here and welcome back to our Searching and Sorting Algorithms Part 2. Today we will be talking about binary search in its recursive form. Let's go over how to implement recursive binary search. Unlike the iterative version, recursive binary search calls itself with updated parameters each time. Let's break it down step by step. So, step 1, the base case. The first thing to handle in any recursive function is the base case. In binary search, the base case occurs when the left index exceeds the right index. This condition tells us that we've searched the entire array but haven't found the element. So in this case, we return -1 to indicate that the target was not found. This is crucial for stopping the recursion, otherwise an infinite loop will occur. So, for step 2, it is about obtaining the mid-index or the middle index. To calculate the mid-index of the current searching range, the formula we use is the same as the formula used in the iterative binary search. This gives us the middle element of the current range. It's important because the entire algorithm revolves around comparing the middle element to the target value. Step 3. Comparing the mid to the target. Once we have the midpoint, we compare the middle element of the current search range to the target. And here's what we're checking. If the middle element matches the target, we will return the index of the middle element because we found the target. If the middle element is greater than the target, we need to look into the left half of the array. If the middle element is less than the target, we will search the right half of the array. This comparison guides us to the next step of our search process. Step 4. Recursive function calls. Now, instead of using a loop like in the iterative form of binary search, we call the binary search function recursively, with the updated range as parameters. So depending on the comparison, each recursive call narrows down the search range just like a loop would in the iterative version. But here we're just using function calls. Let's walk through the code for recursive binary search. We will go step by step to see how each part works and how the recursion helps us search the array efficiently. We will start with the method signature. Here we can see 4 parameters that are required to call the search method. The first is the array that we are searching, and the second parameter is the target element that we are trying to find in the array. The left parameter is the starting index of the current search range, and lastly, right is the ending index of the current search range. Next, we define the base case of the recursion. This is the condition that stops the recursion. If left exceeds right, it means we've searched the entire range and didn't find the target. So we return -1. This prevents the recursion from going on forever when the target isn't in the array. Next, we will calculate the middle index of our current search range by using this particular calculation. Now comes the comparison part. If the element at the middle index is equal to the target, we have found our target, so we will return the middle index. This means that the search is successful and we will stop our process here. If the middle element is greater than the target, this means that the target must be in the left half of the array, so we make a recursive call to search the left half, updating the right index to the element just before middle index. We reduce the search range but continue looking for the target in the left portion of the array. If the middle element is less than the target, in this case, the target must be in the right half of the array. So we call the search function recursively updating the left index to the index just after our middle index, and continue searching in the right portion of the array. Notice how we're not using a loop here. Instead, the recursive function keeps calling itself, narrowing down the search range until it either finds the target or the search range becomes invalid when left exceeds right. Let's look at the visualization example below. For the following example, we can see an array with elements which are already sorted in a non-decreasing order. We can see the three variables left, mid, and right pointed to their respective indices. Left would point to 0 since all arrays start with the index 0. To obtain the right or the last index of our array, we can just subtract 1 from the length of our array. In this case, we are looking for the target 1 from this array. So when we calculate or find the middle element of the array, we obtain the value 5. When comparing it to our target, we can determine that we won't be checking the right half of the array. Therefore, the following condition will turn out to be true. Here is the divided section of our array. Here we could see our left half and the right half. Since we are looking for the target 1, we will not be looking or checking through the right half of our array, and therefore the left half becomes our current searching range. When setting left and right boundaries, we will have to take great care so that we won't get inaccurate or invalid results whenever we are using our binary search algorithm. Here is our array after being divided into two halves. And we can see that the index 2 is our former middle index. And when trying to set boundaries to search the left half, we have to make sure that the right boundary is at the index just before mid. Therefore, our right boundary must be 1 in this case. Now we know that we will not be checking the right half of our array. We will be switching our searching range to the left half of our array. So our right boundary becomes 1. Hence, when we calculate for our middle index by using the new left and right indexes or our new left and right values, we will get 0. And therefore, our left and mid variables will point to the same number. And we can see that our middle element in our current searching range is 1. Whenever we compare it to our target, we can see and determine that we will be searching for our target in the right half of our current searching range. We will have to keep in mind that our current searching range refers to the portion of the array starting from left to right. After the comparison, this following statement would be triggered to set the boundaries to search the right half of our searching range. So, just as the previous step, when trying to set boundaries to search the right half, we have to make sure that our left boundary is the index just after our middle index. After setting the boundaries and calculating the middle index, we can see that all three variables are pointing to the same index. So when we check our middle element to our target element, we can see that it equals to our target. So we will return our index 1. Now let's talk about the recursive binary search time complexity. Like the iterative version, the time complexity of binary search is O of log n. For the best case, when the target is located at the middle of the array, it will be constant time, meaning it will be big O of 1. For the average case, we can see that our time complexity is O of log n. For the worst case scenario, when the target does not exist or when the target is at the end of the array, it will be O of log n. Now let's talk about space complexity. The space complexity of recursive binary search is O of log n, due to the nature of recursion. Unlike the iterative version, which uses constant space, the recursive version of binary search creates a new stack frame for each recursive call. Each call keeps track of the left, right, and mid variables. Since the array is halved, with each recursive call, the maximum number of recursive calls we'll make is log n. This means there are log n stack frames on the call stack at any point. Each recursive call uses constant space to store variables like the left, right, and mid variables. However, because recursion uses the call stack, the total memory use depends on the depth of the recursion, which is O of log n. Now let's compare the space complexity between the recursive binary search and the iterative binary search. The iterative version of binary search has a space complexity of O of 1. Because it doesn't use recursion and doesn't add extra stack frames. But in recursive version, the function call stack grows with each recursive call, making the space complexity O of log n. Now let's write the code for our recursive binary search. It will require the parameters. Here will be the array. Here's the target value, and here will be the left boundary, and here will be the right boundary. First, we will add our base case. If our left is greater than our right boundary, we will return -1, indicating that our search was unsuccessful. Otherwise, we will compare it, but first we will have to calculate our middle index, which can be obtained by combining left and right and dividing it by 2. And we will start comparing with our target element. If it's equal, we will return our index, indicating that our element is now found. If the middle element is greater than our target, we will have to return another recursive call to search for the other half of the array, which will be the left half of our array. Else, we will return another recursive call to the right half of our array. To test our algorithm, we will create a new array . We will search for the value 10. Left would be 0 by default, and right would be the last index of our array. Let's see if it works. Yes, it does. If you enjoyed this video and found it helpful, please give it a thumbs up and subscribe for more content. If you have any question or topics you would like me to cover, feel free to leave a comment below. I would love to hear your thoughts. Thanks for watching, and I will see you in the next video.